Rotational inertia depends on the quantity of matter, or the mass, and the mass distribution. So if we're looking at a single point mass, a distance r, from the axis of rotation, the rotational inertia, our moment of inertia, is going to be defined as I equals mr squared. So the value of that mass times the distance from the axis squared. Now, if we have a system with multiple point masses, in that case, that rotational inertia is the sum of mr squared for every single point mass. So you'll do mr squared for the mass and location of one point mass, and then plus mr squared for a second point mass, so on and so forth. The next key idea, the further away the mass is from the axis of rotation, the greater the rotational inertia will be. So in this case, we have two examples. In case 1, we can call this distance r1. We have two masses away from the axis of rotation, and they are both at a radius of r1 away from the axis of rotation. In the second example, it's a similar setup, 2 point masses, but now they're a distance r2 away from the axis of rotation. And visually, if this is to scale, we can see that r1 is greater than r2. Okay, so r1 is greater than r2. That means, since we know the moment of inertia is proportional to that distance squared, that means I1 should be greater than I2. So the moment of inertia in case 1 is greater than the moment of inertia in case 2, which means the greater the moment of inertia, the greater the resistance to change. So the greater the I, the greater the resistance to change. And of course, that's to change for the angular acceleration. So it's going to be slower to start moving or slower to stop moving.